When we look up at the night sky, most of us see nothing more than a canvas of glittering stars, a backdrop that feels eternal, predictable, and unchanging. Yet in reality, the universe is anything but static. The cosmos is alive with movement. Planets orbit their stars, galaxies drift across unimaginable distances, and hidden among these familiar motions are occasional visitors that defy all expectations. Every so often, something crosses into our solar system that forces us to reconsider what we think we know about the nature of the universe. These are not the familiar comets that streak across our skies with icy tails, nor the asteroids we catalogue and predict with mathematical precision, but strangers from the deep reaches of interstellar space. Their journeys have taken them across billions of miles and millions of years, and when they arrive here, they bring with them mysteries that challenge even the most seasoned astronomers. To introduce the significance of such phenomena, one must return to a moment in 2017 when an object unlike any seen before burst onto the scene. What made it remarkable was not just its speed or its trajectory, but its very nature, one that sparked debates that remain unresolved to this day. Its arrival was more than a simple scientific discovery. It was a cosmic shockwave that pushed humanity to expand its search for answers and accelerate efforts to understand what else might wander into our celestial neighborhood. The first confirmed interstellar object, later named ʻOumuamua, showed us that our solar system is not isolated. Instead, it is part of a dynamic galactic ecosystem where rocks, ice, and potentially stranger materials are exchanged between star systems. The implications of this are vast, for it means that fragments of other planetary systems drift into our reach, carrying clues about their birthplaces and histories. These clues are like messages written in a language of chemistry and physics, waiting for us to decipher them. With ʻOumuamua came the realization that we had to be prepared not only to observe, but to respond, because these visitors appear suddenly and vanish just as quickly. In fact, by the time astronomers had realized what they were looking at, the object was already on its way out, receding into the darkness, beyond the reach of even our most powerful telescopes. That fleeting glimpse ignited discussions that ranged from natural explanations rooted in unusual astrophysics to the tantalizing, if controversial, possibility of engineered origins. But more importantly, it forced humanity to admit that we were unprepared. From that moment on, the field of astronomy experienced a shift. What had once been a theoretical prediction that interstellar objects must exist suddenly became an observational reality. Scientists knew we needed better sky surveys, faster response times, and global cooperation to avoid missing future discoveries. And so began a new chapter in planetary defense and cosmic exploration, one defined by networks of telescopes capable of scanning the heavens every night in search of anything out of place. These systems, designed to protect us from potential asteroid impacts, suddenly became our best tools for spotting interstellar travelers. Their mission expanded from defending Earth to unraveling the mysteries carried by these cosmic wanderers. The introduction to this story is not simply about the science of astronomy, but about humanity's place in the universe. For centuries, we believed our solar system to be the center of our cosmic narrative. The discovery of planets around other stars broadened that view, but it remained abstract. Interstellar objects made it personal. They are not distant points of light observed through indirect measurements. They are physical messengers arriving in our backyard, carrying the raw materials of alien worlds. Every fragment of dust, every molecule of gas they release, becomes a data point in the grand story of planetary formation across the galaxy. With each discovery, we are not just learning about an object, we are piecing together a galactic puzzle that connects our star system to countless others. This is the beginning of a narrative that is as much about our own curiosity as it is about the cosmos itself. To prepare for what lies ahead, we must embrace the fact that the universe is not a static backdrop, but a stage of constant motion and exchange. Interstellar objects are proof of that dynamism. They are reminders that the galaxy is not just a collection of isolated systems, but a web of interconnected journeys, with material flowing endlessly between stars. And within that flow may lie answers to the most profound questions of all: how planetary systems form, how organic molecules spread, and perhaps even whether life itself has traveled across these cosmic highways. What began in 2017 as a moment of surprise has grown into a story of preparation, discovery, and anticipation as we stand ready to welcome the next visitor from beyond the stars. On July 1st, 2025, a routine night of sky monitoring turned into something extraordinary when astronomer Larry Deno submitted what initially looked like just another faint moving dot in the crowded star fields. It appeared unimpressive at first glance, registering a magnitude of 18.8, which made it millions of times dimmer than the North Star. Yet, this faint glimmer carried with it signs that would soon shake the astronomical community. Its motion across the sky was not the slow, predictable drift expected of an asteroid or near-Earth object. Instead, it moved with an urgency, a purposeful trajectory that made astronomers pause. When preliminary calculations were run, the numbers suggested this object was not bound to our sun. That single fact changed everything. If true, it meant this was not simply another rock in orbit, but something that had come from beyond our solar system, a visitor from the great cosmic sea that stretches between the stars. The system that detected this anomaly was ATLAS, a global network of telescopes designed to scan the skies each night for potential threats to Earth. Its primary purpose has always been planetary defense, identifying asteroids and other objects that could pose an impact risk. ATLAS works by capturing repeated images of the same portions of sky and comparing them to detect motion. Thousands of objects are flagged daily, most of them routine, familiar asteroids with orbits we already understand. But every now and then, something stands out. That night, the algorithms passed the detection along for human review, and what Deno noticed was not its brightness or size, but the unusual speed and angle of motion. It didn't fit into the normal categories of celestial wanderers that orbit within our solar system. As the alert spread, telescopes around the world turned toward the coordinates. The Catalina Sky Survey in Arizona quickly joined in, providing confirmation images that showed the dot sliding against the backdrop of distant stars. The Minor Planet Center initially catalogued it as A1Pi3Z, a standard designation for a near-Earth object, awaiting classification, but as data streamed in, it became increasingly obvious that this was no routine find. Its velocity relative to the Sun was measured at 66 kilometers per second, a speed that placed it far beyond the escape velocity of the solar system. This meant it was not gravitationally bound to our star and would never settle into an orbit. Instead, it was merely passing through, destined to swing around the Sun once before vanishing forever into the abyss. The European Space Agency's Planetary Defense Team quickly mobilized their resources, tracking the object with powerful telescopes in Spain and Chile. They refined the trajectory with each new observation, and the picture became clear. This was an interstellar object, the third of its kind ever confirmed, after the 2017 detection of ʻOumuamua and the 2019 discovery of Borisov. The news electrified the astronomical community. Professional astronomers scrambled to secure emergency telescope time, aware that such opportunities come once in a generation. Amateur astronomers shared coordinates across forums and social media, ensuring a global network of sky watchers could follow the event. Suddenly, what had been a faint dot in one telescope became a worldwide effort to study a cosmic stranger. The early discovery phase was marked by excitement, but also urgency. Unlike most comets or asteroids that linger for years or even centuries in predictable orbits, interstellar visitors give us only a short window of observation. ʻOumuamua had slipped past Earth unnoticed until it was already receding into space, leaving astronomers scrambling to gather data. With this new discovery, there was no time to waste. Observatories raced to capture spectra, measure brightness changes, and record every detail that might reveal its composition and origin. Citizen scientists contributed by combing through archival data, finding earlier appearances of the object weeks before its official detection. These pre-discovery sightings allowed astronomers to refine their calculations, reducing uncertainties and confirming beyond doubt that this was indeed a visitor from another star system. The significance of the initial discovery lies not only in its scientific value, but in the way it demonstrated the progress made since 2017. Back then, the world was caught off guard. Now, in 2025, the systems were better prepared, the networks more connected, and the community more responsive. This readiness ensured that what could have been a fleeting mystery became instead an opportunity for deep study. The faint dot recorded on July 1st was no ordinary object. It was a messenger from beyond, carrying secrets locked in its icy core, secrets forged in a distant star system perhaps millions of years ago. For astronomers, the discovery phase marked the beginning of a race against time, a race to learn as much as possible before this interstellar traveler disappeared back into the void, leaving behind only the data and the wonder it inspired. When astronomers first confirmed the trajectory of the mysterious object that would later be named 3IATLAS, the next step was to unravel the details hidden in its earliest appearances. The official detection on July 1st, 2025 was remarkable, but its story had actually begun days earlier, unnoticed, as faint points of light recorded in astronomical archives. The breakthrough came not from a major observatory, but from the perseverance of a citizen scientist, Sam Dean. Working late into the night, Dean scoured weeks of raw Atlas survey data, combing through countless images of the sky in search of anything that might align with the newly discovered visitor. His determination paid off when he uncovered a trail of observations dating back to June 25th. What looked at first like a string of faint, nearly insignificant dots turned out to be a breadcrumb trail of the interstellar object's earlier journey across the heavens. These pre-discovery observations proved invaluable. Instead of working with just a handful of hours of tracking data, astronomers suddenly had nearly a week's worth of positions to feed into their calculations. This reduced the uncertainty in the orbital models from broad guesses to precise trajectories, confirming beyond all doubt that this object was not from within our solar system. But the revelations did not stop there. Building on Dean's work, astronomer Yi extended the timeline even further by combing through the Zwicky Transient Facility's archives, uncovering evidence that pushed the earliest observations back to June 14th. This extended tracking window meant astronomers now had nearly 3 weeks of positional data. With this, the mathematics became undeniable. The object's orbit showed an eccentricity of 10.4, an extreme value far exceeding anything seen before. For context, Earth's orbit has an eccentricity close to 0, making it almost a perfect circle. Even the most elongated comets in our solar system rarely exceed eccentricities of 3. An eccentricity greater than 1 already marks an object as unbound, traveling on a hyperbolic trajectory that ensures it will pass through the solar system once and never return. But 10.4 was something entirely new, a record-shattering number that spoke of unimaginable speed and a violent ejection from its home system. This discovery stunned seasoned astronomers who understood the implications. The mathematics painted a clear picture. 3IATLAS had been launched into interstellar space millions of years ago, possibly by catastrophic events such as gravitational slingshots with massive planets, or even the explosive death of a star. The sheer velocity was staggering. At 66 kilometers per second relative to the Sun, this object was moving faster than either ʻOumuamua or Borisov, the two earlier confirmed interstellar visitors. To put this into perspective, at that speed, one could cross the continental United States in under 2 minutes. Such velocity was far beyond anything natural objects within our solar system could sustain on their own. It confirmed that this visitor had been shaped by cosmic forces of immense scale, carrying with it a history written in its speed and trajectory. The data also revealed its incoming path, which traced back toward the direction of the constellation Sagittarius, pointing generally to the galactic center. This was a tantalizing clue, for that dense region of the Milky Way is home to countless stars and gravitational influences that could easily have ejected an object like this into the cosmic wilderness. Each refined calculation brought astronomers closer to understanding the journey of 3IATLAS, transforming what began as a faint moving dot into a messenger from across the galaxy. The excitement was palpable not just because of its origin, but because of what it meant for science. The discovery of a third interstellar object in just a few years was confirmation that such visitors were not rare flukes, but regular occurrences. This realization changed the field entirely. Instead of asking whether interstellar objects might pass through our solar system, astronomers now asked how often they appeared and what secrets they carried with them. Professional observatories quickly recognized the unprecedented nature of the find. The International Astronomical Union moved with rare speed to formally designate the object 3IATLAS, cementing its place in history alongside its two predecessors. The name carried a fitting symbolism. Atlas not only honored the survey system that first detected it, but also evoked the ancient Titan who bore the heavens on his shoulders, a cosmic traveler carrying secrets from a distant world. For astronomers, the pre-discovery phase represented far more than just a technical detail. It was proof of how modern astronomy thrives, not only on massive telescopes, but also on the dedication of individuals willing to sift through archives, connect the dots, and push the boundaries of knowledge. Sam Dean's discovery underscored a truth that would define this era of science. The cosmos is too vast for any single institution to explore alone, and sometimes the most profound contributions come from those working outside the traditional walls of academia. The identification of those earlier observations was a turning point. What had been a remarkable but fleeting sighting became a fully confirmed interstellar visitor with precise orbital parameters. It marked the moment the astronomical community shifted from surprise to preparation. This was no longer just about discovery, it was about mobilization, collaboration, and racing against time to study an object that would soon vanish forever into the depths of interstellar space. In that sense, the early tracking of 3IATLAS was both a triumph of mathematics and a testament to the persistence of human curiosity, proving once again that the universe rewards those who are willing to look a little closer. When astronomers finally had precise orbital calculations of 3IATLAS, the next phase was understanding just how extraordinary its speed and path through the solar system really were. What immediately stood out was its velocity, 66 kilometers per second relative to the Sun, a speed far greater than the escape velocity of the solar system, which is only about 42 kilometers per second. In simple terms, nothing born within the boundaries of our star's gravitational influence should be moving that fast, unless it had been violently expelled. For comparison, most comets and asteroids follow predictable elliptical orbits that keep them bound to the Sun, even when they travel out past Pluto. Even the most extreme long-period comets, which take thousands or even millions of years to complete an orbit, remain gravitationally tethered. But 3IATLAS is different. It is unbound, destined to visit once and then continue its journey into the darkness, never to return. The object's eccentricity, calculated at an unprecedented 10.4, reinforced this conclusion. In astronomy, eccentricity is the number that describes how circular or elongated an orbit is. An eccentricity of 0 is a perfect circle, while anything between 0 and 1 is an ellipse. An eccentricity of exactly 1 is a parabolic escape, while anything greater than 1 is hyperbolic. Hyperbolic trajectories mean the object is a visitor. It will swing around the sun only once before being flung out forever. ʻOumuamua, the first confirmed interstellar object detected in 2017, had an eccentricity of about 1.2, and Borisov, discovered in 2019, had about 3.4. Both were extraordinary in their own right, but 3IATLAS dwarfed them in extremity. At 10.4, it wasn't just interstellar, it was on a path so steep that it seemed to almost glance off the solar system, like a stone skimming across water. This incredible trajectory raised profound questions about how it had been accelerated to such speeds. The most plausible explanations involve violent gravitational encounters in its home star system. It could have passed dangerously close to a massive planet or binary stars, receiving a slingshot powerful enough to eject it into interstellar space. Another possibility is that it was expelled during the death of a star, perhaps in the shockwave of a supernova, where the release of energy is powerful enough to hurl surrounding material across the galaxy. Whatever the cause, its speed made one thing clear: this object had a violent history. It was not a quiet traveler, but the product of catastrophic cosmic forces carrying the scars and chemistry of that ancient event. The direction of its approach added another layer of intrigue. The refined data showed that it had entered from the constellation Sagittarius, near the galactic center, one of the most densely populated regions of stars in the Milky Way. That suggested it had traveled through some of the most chaotic and gravitationally active regions of the galaxy. Over millions of years, as the Milky Way itself rotates and star systems shift relative to each other, 3IATLAS would have crossed paths with countless stars, each tugging gently at its path. But the fact that it still reached our solar system with such staggering speed suggested its initial ejection was extremely forceful. This wasn't the trajectory of a wandering asteroid randomly nudged from its home. It was the cosmic equivalent of a bullet fired from a cannon. What fascinated scientists most was not only the object's speed, but what it meant for our broader understanding of the galaxy. Until the 21st century, interstellar visitors were purely theoretical, their existence assumed but unproven. Then came ʻOumuamua, a mysterious, elongated body that defied easy classification. Then Borisov, an interstellar comet that behaved much like the icy bodies we already knew. And now 3IATLAS, a record-breaking traveler, moving faster and following a path more extreme than anything astronomers had ever documented. 3 detections in under a decade transformed the narrative. Interstellar objects were not rare, once-in-a-lifetime flukes. They were regular messengers, slipping through our solar system with some frequency, most of them going unnoticed until our detection systems grew sophisticated enough to catch them. This revelation carries enormous implications. It means that material from other star systems passes through our own neighborhood more often than we once believed, offering rare opportunities to study the chemistry, physics, and history of alien worlds without leaving our solar system. Each visitor is a time capsule, carrying within it the frozen remains of its birth system, shaped billions of years ago and preserved by the deep cold of interstellar space. With 3IATLAS, its speed and extreme trajectory mean its time here is fleeting. but also that the event propelling it was powerful enough to imprint a unique story into its path. Astronomers quickly realized that such high velocity would make it impossible to capture or redirect the object for direct exploration. Unlike a comet bound to the Sun, which can be studied over repeated passes, this interstellar traveler offers only one brief chance. It will swoop past the Sun, bend slightly under its gravity, and then accelerate even faster on its outbound journey, fading into the void. That urgency has fueled a global rush to study it while it remains visible. Every major telescope network, from ground-based observatories to space-based instruments like the James Webb Space Telescope, has turned its attention toward the faint dot racing across the sky. The trajectory of 3IATLAS is more than just a mathematical curve. It is a message from another world. Its speed tells us of violent encounters long ago. Its path points us toward its possible origins, and its fleeting visit reminds us that the universe is not static, but alive with travelers, some of them carrying secrets we may never have imagined. In unraveling its movement, astronomers are not just tracking an object, but piecing together a cosmic story that began millions of years ago, somewhere in the crowded heart of the galaxy, and has now intersected briefly with our own small corner of the cosmos. When scientists pieced together the earliest archival data of 3IATLAS, what initially appeared to be a faint moving dot in the star fields suddenly became one of the most astonishing interstellar objects ever documented. The breakthrough came from the meticulous work of both professional and amateur astronomers, who scoured survey data and uncovered pre-discovery images dating back nearly 2 weeks before its official detection. These additional observations dramatically reduced uncertainties in the calculations, shrinking the margins of error and allowing astronomers to confirm with confidence that the object was on a hyperbolic trajectory, unbound from the Sun and entering the solar system from interstellar space. The eccentricity measured at 10.4 was unlike anything astronomers had ever seen. To put that in context, Earth's orbit has an eccentricity close to zero, meaning nearly circular, and even the most elongated comets within our solar system rarely surpass 1. A value of 10.4 wasn't simply unusual, it was unprecedented, so extreme that it instantly ruled out any possibility of the object being local. It was the astronomical equivalent of spotting a traveler on a freeway moving far faster than anything the local traffic could ever achieve, proving it must have come from somewhere else entirely. As this reality sank in, excitement spread quickly through the astronomical community. Here was only the third confirmed interstellar object in history, following the enigmatic ʻOumuamua in 2017 and comet Borisov in 2019. But unlike those earlier visitors, 3IATLAS was larger, faster, and more extreme in every measurable way. Its speed, clocked at 66 kilometers per second relative to the Sun, exceeded the already record-breaking velocities of its predecessors. To put that number into perspective, at such speed, one could travel from New York to Los Angeles in less than 2 minutes or circle Earth in just over 10 minutes. Nothing born inside the solar system could move so quickly unless it had been hurled outward by violent gravitational encounters or stellar explosions. Its hyperbolic trajectory told an even more compelling story. This was not a quiet wanderer nudged from its orbit, but the result of powerful forces that expelled it from its home system millions of years ago. The object's arrival from the direction of the constellation Sagittarius only deepened the intrigue. That region lies near the dense galactic center, where gravitational interactions are far more common due to the sheer concentration of stars and massive celestial objects. It is entirely plausible that 3IATLAS was born in the cold outer regions of a planetary system there, only to be violently ejected during chaotic early development or by the disruptive forces of a nearby stellar encounter. Over millions of years, it traveled through interstellar space, enduring freezing temperatures near absolute zero, constant bombardment by cosmic rays, and unimaginable stretches of emptiness. And yet it survived intact, carrying with it a chemical fingerprint of its origin, a sample of alien planetary formation processes preserved in its frozen core. For astronomers, what made this discovery thrilling wasn't just the mathematics of its orbit, but the implications. Each interstellar visitor is essentially a messenger from another star system, a physical sample from a place humanity could never hope to reach with spacecraft in any reasonable time frame. ʻOumuamua, elongated and strangely accelerating, sparked debates about whether it was a comet, an asteroid, or something more exotic. Borisov, on the other hand, behaved very much like a typical comet, complete with gas and dust tails, offering confirmation that icy bodies form around other stars in ways similar to our own. Now 3IATLAS arrived, larger and faster than both, providing scientists with a fresh chance to test theories about how planetary systems eject material and how these cosmic exiles survive their long interstellar journeys. The urgency of the moment became apparent quickly. Because of its extraordinary speed and steep trajectory, 3IATLAS would only remain within observational reach for a short time before vanishing forever. Astronomers around the world scrambled to secure telescope time, knowing they were witnessing a once-in-a-generation event. Every hour mattered, and the global community coordinated to track the object across different time zones and hemispheres. Professional observatories in Chile, Hawaii, Arizona, and Spain all contributed data, while amateur astronomers added valuable observations of their own. This collaborative effort created one of the most detailed portraits of an interstellar visitor ever assembled. But beyond the scientific thrill, 3IATLAS also carried a symbolic weight. It was a reminder of just how dynamic and interconnected the galaxy truly is. For centuries, people looked at the night sky and imagined it as a distant, unreachable backdrop. Yet here was a piece of another star system, not in theory but in reality, passing through our neighborhood. Its presence suggested that the Milky Way is full of such wanderers, quietly slipping past, most too faint to detect. The fact that 3 had been found in less than a decade pointed to an exciting new era where improved telescopes and detection systems would transform these rare discoveries into more regular opportunities. Each visitor would bring with it a new story, a new set of data, and perhaps one day direct evidence of the chemistry that leads to life itself. In the case of 3IATLAS, its trajectory and speed told astronomers that it was not just another visitor, but a record-breaker, proof that the galaxy is far more dynamic, violent, and full of exchanges than we might have imagined. It was not here for long, but its path etched a permanent mark in the history of astronomy, opening the door to questions that would shape our understanding of interstellar travel, planetary formation, and the endless possibilities of a universe alive with motion. The realization that 3IATLAS was unlike anything previously observed ignited an unprecedented wave of excitement across the global astronomical community. But the real turning point came when professional and amateur astronomers began working together to reconstruct its past. Citizen scientists digging into archived datasets found that the object had been captured by telescopes days, even weeks, before its official discovery, but its presence had gone unnoticed because of its position in front of the galactic center, a region so densely crowded with stars that it was nearly impossible to pick out faint moving objects. These rediscovered images provided crucial pre-discovery data that extended the timeline of observations and made the orbital calculations far more precise. Suddenly, what was once a mysterious dot moving across a noisy star field became a well-defined interstellar traveler with a hyperbolic path that left no doubt about its alien origin. This collaboration highlighted the way astronomy has shifted in the 21st century, no longer the domain of only large observatories, but a shared endeavor where amateur passion and professional resources intersect to create extraordinary discoveries. The technical details themselves were staggering. With more observational data added, astronomers calculated an eccentricity of 6.3, far beyond the critical threshold of 1 that distinguishes bound objects from unbound ones. To put that into context, Earth's orbit is nearly circular, with an eccentricity of just 0.0117, and even elongated comets like Halley's measure under 1. A value of 6.3 is extreme to the point of rewriting expectations. It means 3IATLAS is traveling on one of the most open hyperbolic trajectories ever documented, and nothing in our solar system could have produced such a violent path. Only a catastrophic ejection mechanism, a gravitational slingshot from a giant planet, a near pass with a star, or even the aftermath of a supernova could account for this extraordinary speed and trajectory. Every calculation confirmed that this was not an eccentric comet returning from the Oort cloud, but a visitor born in another star system, millions of years and light years away. Yet, the most remarkable aspect wasn't just the numbers, but the window of opportunity they opened. With its perihelion predicted for late October 2025, 3IATLAS would pass safely inside the orbit of Mars while maintaining a vast distance from Earth. This meant it posed no threat whatsoever, but it also meant that it would never return. Its hyperbolic path was a one-way journey into the solar system, past the Sun, and out again, faster and farther than ever before. Astronomers had a fleeting chance to gather as much data as possible before it disappeared into interstellar darkness. Telescopes across the globe were scheduled around the clock to track its brightness, study its coma and tail, and collect spectra that would reveal its chemical composition. The James Webb Space Telescope was called into action, turning its advanced infrared eyes on the object to capture thermal emissions and identify volatile compounds as they sublimated under the sun's heat. Meanwhile, the European Southern Observatory and other facilities planned coordinated spectroscopic campaigns to map its activity as it brightened and dimmed. This coordination was essential because 3IATLAS would not remain observable for long. Its approach took it close to the sun in Earth's skies, limiting visibility due to glare, and by September it would vanish behind the sun entirely. When it re-emerged in December, it would already be receding, dimmer and less active, a fading spark on its way back into the void. The narrow observation window added urgency and drama to the discovery. Astronomers had to work quickly, coordinating globally, sharing data, and ensuring every available instrument was trained on the visitor. Never before had so many telescopes focused simultaneously on an interstellar object. And never had the collaboration between amateurs and professionals been more crucial. This sense of urgency also underscored how fragile such opportunities are. For every 3IATLAS detected, there may be dozens or hundreds of interstellar visitors that pass unnoticed, either too small, too faint, or hidden against the wrong patch of sky. The fact that this one was nearly missed due to the galactic center's crowded backdrop demonstrates both the limits of current detection methods and the importance of vigilance. The upcoming Vera C. Rubin Observatory promises to change that, scanning the southern sky with unprecedented sensitivity and cadence, making it likely that such discoveries will become more frequent. But in 2025, 3IATLAS was still a rare cosmic messenger, one that required the entire community to mobilize to catch every possible detail before it slipped away forever. For the public, the story carried its own sense of awe. Here was an object, not just from the farthest reaches of our solar system, but from another star system entirely, passing through our neighborhood for the first and only time. It was a tangible reminder that we are not isolated, that material from other worlds is constantly passing nearby, carrying secrets of planetary formation, chemistry, and perhaps even the building blocks of life. For scientists, it was an extraordinary chance to peel back layers of cosmic history. And for ordinary people, it was a humbling reminder that the galaxy is alive with motion, filled with wanderers that sometimes pass close enough for us to glimpse them before they continue their eternal journeys. 3IATLAS was not just an astronomical event, it was a story of discovery, collaboration, and the relentless curiosity that drives humanity to look up and wonder. What made 3IATLAS stand apart from the previous two interstellar visitors, ʻOumuamua in 2017 and Borisov in 2019, was not just its extraordinary speed or eccentricity, but its sheer size and behavior, which immediately elevated it into a category of its own. While ʻOumuamua was relatively small, only a few hundred meters long at most, and Borisov's nucleus measured between 400 and 500 meters in diameter, 3IATLAS appeared to be on an entirely different scale. Early brightness measurements indicated an absolute magnitude of about 11.9. That number may not sound like much on its own, but translated into physical dimensions, it implied that if the object were a dark, inactive asteroid, it could be as large as 20 to 24 kilometers across. Because 3IATLAS was clearly an active comet, surrounded by a reflective coma of gas and dust, the nucleus was certainly smaller than those rough estimates, but even the most conservative calculations suggested that it was many times larger than both of its predecessors. Astronomers realized almost immediately that they were looking at a giant, possibly 10 times the size of Borisov, an interstellar visitor unlike any they had ever seen. The implications of such a massive interstellar comet are profound. Ejecting a small asteroid into interstellar space requires significant gravitational energy, but ejecting something as large as 3IATLAS suggests an almost unimaginably violent event in its birth system. It could have been launched outward by a series of close encounters with giant planets migrating through their early orbits, or even by interactions with binary stars, where complex gravitational dynamics can throw massive objects into hyperbolic escape. Another possibility is that it was flung outward during the death throes of a star, when a supernova explosion or other catastrophic stellar event imparted enough momentum to send it hurtling into the cold void between star systems. Whatever the mechanism, the fact that something this large could be expelled, survive millions of years of deep space travel, and still arrive intact in our solar system tells scientists that the processes shaping planetary systems are even more dynamic and violent than once thought. The larger size of 3IATLAS also makes it scientifically invaluable. Bigger comets tend to contain more diverse chemistry and preserve a wider record of their formation history. Layers deep within the nucleus may have remained untouched since the object's original formation, billions of years ago, preserving pristine samples of material from its home star system. As the sun's energy begins to heat the surface and trigger outgassing, astronomers have the opportunity to analyze gases and dust that could reveal the chemical environment of an alien world-building disk. Spectroscopy of its coma has already hinted at similarities with comets from our own Kuiper belt, but subtle differences in isotopic ratios or trace molecules may point to conditions unique to its origin. For scientists, this represents a rare, perhaps once-in-a-lifetime chance to study the raw materials of another planetary system without having to send spacecraft across light years of space. But size comes with challenges as well as opportunities. Determining exactly how large 3IATLAS is remains difficult because its coma, an expanding cloud of gas and dust, dramatically increases its apparent brightness, making it nearly impossible to directly observe the nucleus. This is where advanced technology becomes critical. Infrared instruments aboard the James Webb Space Telescope can separate the heat signatures of the solid core from the reflected sunlight of the surrounding dust. Radar observations, though technically challenging at such great distances, could eventually provide a more direct estimate of the nucleus's size and even its shape. If such measurements succeed, they would offer the most accurate physical characterization of an interstellar visitor ever achieved. The potential size of 3I/ATLAS also forces astronomers to rethink how common such large interstellar objects might be. Until recently, the assumption was that only relatively small comets or asteroids could be ejected into interstellar space in significant numbers, because larger ones would require so much energy. But if 3I/ATLAS is representative of a class of giant interstellar comets, then the galaxy may be far more populated with such travelers than previously imagined. Each discovery reshapes statistical models of how many objects are out there and what sizes they might be, and 3I/ATLAS has already forced a dramatic upward revision of expectations. For the general public, the news that such a massive object was passing through our cosmic neighborhood could have been alarming, but astronomers quickly reassured everyone that 3I/ATLAS posed no danger. Its trajectory placed it safely inside Mars's orbit, but far away from Earth's path, and because of its hyperbolic orbit, it will never return. Instead, it offers a rare chance to study a giant from another star system, a visitor carrying chemical secrets from its birthplace and telling a story written long before humans ever looked up at the night sky. In the end, its immense size is both a scientific blessing and a humbling reminder. The galaxy is not only filled with countless stars, but with vast wanderers, larger and more powerful than anything we imagined, silently crossing the void until chance brings them briefly into view. What makes 3I/ATLAS particularly fascinating beyond its speed, eccentricity and size is the story of its survival. For this cosmic wanderer has endured conditions that would destroy almost any material on Earth. To appreciate the resilience of such an object, one must imagine what it means to drift for millions of years through the void between stars. Temperatures in interstellar space hover near absolute zero, roughly 270 degrees Celsius, so low that atomic motion within molecules slows to almost nothing. Chemical reactions cease, and most substances become brittle beyond recognition. For an object like 3I/ATLAS, composed largely of ice and dust, such conditions are both a curse and a blessing. On the one hand, they expose the surface to freezing desolation and constant cosmic radiation. On the other hand, they preserve the deeper layers of the nucleus in pristine condition, essentially freezing in time the chemical makeup of the world it came from. Radiation represents the second challenge. High-energy cosmic rays, the remnants of ancient supernovae, zip through the galaxy at near-light speeds, striking everything in their path. When they hit an interstellar comet like 3I/ATLAS, they can break apart molecular bonds, alter chemical structures, and even penetrate meters into the surface layers. Over millions of years, the upper crust of such an object can become heavily processed, darkened, and hardened, forming a kind of shield. Yet that very shield can protect the interior, ensuring that the ices and organics buried within remain as untouched as when they first formed. This dual effect, destructive on the surface but protective below, may be one of the reasons why interstellar objects like 3I/ATLAS remain scientifically invaluable, carrying unaltered samples of alien chemistry inside them. The very fact that 3I/ATLAS is now outgassing as it approaches the Sun confirms that its internal ices have not been entirely depleted by radiation damage or sublimation. For millions of years, it resisted the harshest environments imaginable, only to awaken again under the gentle warmth of a new star. The gases and dust now streaming from its surface represent a direct message from another planetary system, a chance to study what kinds of molecules formed in an alien nursery. If those molecules include complex organic compounds, it strengthens theories that the galaxy is rich with the ingredients for life, and that such materials may be exchanged between systems via comets like this one. Some researchers even speculate that interstellar visitors could play a role in panspermia, the idea that the building blocks of life, or even life itself in microscopic form, could travel across star systems, carried safely in the frozen vaults of comets. Reconstructing the path of 3IATLAS backward in time offers tantalizing hints about where it may have originated. Its trajectory points toward the constellation Sagittarius, not far from the galactic center, a region dense with stars and violent gravitational interactions. Tracing that path requires massive computer models that factor in the orbits of countless stars over millions of years, since every close encounter can nudge an object slightly off course. Data from the Gaia mission, which has mapped the precise positions and motions of over 1 billion stars, is being used to attempt this reconstruction. While uncertainties grow over such long timescales, the models may eventually narrow down candidate star systems that could have birthed 3IATLAS. Theories about its ejection suggest several possibilities. One is a gravitational slingshot from giant planets, which can hurl smaller bodies outward if they pass close enough. Another is a stellar flyby, in which two stars pass near one another and their outer cometary reservoirs are disrupted, sending icy bodies into interstellar trajectories. The most dramatic possibility is a supernova, where the explosion of a massive star could impart enough velocity to fling nearby objects outward like shrapnel. Each scenario speaks to a violent origin, reminding us that planetary systems are shaped not only by steady processes, but also by catastrophic events. In surviving all of this, 3IATLAS demonstrates that material from distant star systems can endure journeys across the galaxy and still carry meaningful scientific information. It suggests that the universe is constantly exchanging matter between systems, blurring the boundaries of where one planetary family ends and another begins. The resilience of this comet tells us that the story of the galaxy is one of shared heritage, where dust, ice, and organics can travel for millions of years only to reveal their secrets when they pass close to a curious civilization orbiting an ordinary star. In studying its survival, astronomers are not only uncovering the history of one interstellar visitor, but also testing theories about the durability of life's building blocks, the violence of stellar environments, and the interconnectedness of the Milky Way itself. Despite its alien origin and record-breaking velocity, 3IATLAS has captured the attention of astronomers worldwide, not because it threatens Earth, but because it offers a fleeting window into the chemistry and behavior of material that formed around another star system billions of years ago. Unlike ʻOumuamua, which confounded scientists with its elongated shape and strange acceleration, or Borisov, which provided the first clear example of an interstellar comet, but was relatively small, 3IATLAS presents itself as a much larger and more active visitor, its behavior aligning neatly with what models predict for icy bodies exposed to the sun after long dormancy in the cold. Early on, telescopes detected the faint emergence of a coma, a thin veil of gas and dust surrounding the nucleus, as frozen volatiles began to sublimate directly into vapor. At first, the coma was subtle, but as weeks passed and the object drew closer to our star, the evidence became undeniable. This was a comet awakening from a sleep that had lasted millions of years. That awakening process is one of the most scientifically valuable stages of its journey, because it exposes pristine ices that may never have been altered since their formation in a distant planetary nursery. The detection of its reddish glow, a telltale sign of dust mixed with complex organics, instantly sparked comparisons with Borisov, whose coma and tail carried similar coloration. The similarity suggests that the processes that create comets may be universal across planetary systems. When stars form, their outer regions accumulate icy bodies rich in carbon compounds, frozen gases, and dust. The release of these materials during a close stellar passage provides a chemical snapshot of alien worlds, encoded in the spectral fingerprints of escaping gases and particles. Astronomers using the Nordic Optical Telescope confirmed that Atlas was shedding material in a way fully consistent with standard comet physics, proving beyond doubt that interstellar objects can behave much like those native to our own solar system. For many, this was reassuring proof that the universe is governed by predictable laws, even when dealing with wanderers from beyond. Yet it also raises exciting questions about whether the similarities extend to more complex molecules, perhaps even precursors to biology. Studying such activity is no easy feat, given how faint the comet remains, hovering around magnitude 18 Boit. Observatories across the globe, from Chile's deserts to Hawaii's volcanic peaks, have coordinated their efforts to collect as much data as possible before the object slips from view. The James Webb Space Telescope adds an unparalleled advantage, able to capture the faint infrared glow of gases and dust with unmatched sensitivity. Each spectral line it detects corresponds to a specific molecule, whether it be water vapor, carbon dioxide, methane, or something more exotic. The presence and relative abundance of these species offer a window into the environmental conditions of Atlas's birthplace. Were the outer regions of its system rich in water ice? Did organic chemistry thrive there in the same way it did in our own Kuiper belt? These are questions only careful spectroscopic analysis can answer, and scientists are racing against time to gather as much data as possible before the comet disappears behind the Sun later this year. As 3IATLAS continues its inward trajectory, its activity is expected to intensify. Jets of gas may erupt from weak points on its surface, feeding the coma and lengthening the faint tail that has already been observed. Each burst reveals not just the composition of the comet, but also the mechanics of how its surface responds to heating. Uneven outgassing can even alter the rotation rate of a comet, as jets act like tiny thrusters, changing the spin and wobble of the nucleus. Monitoring these changes allows astronomers to infer the shape, density, and strength of the object, all of which contribute to understanding how such bodies form and evolve. Observers hope to detect variations in brightness that could reveal the comet's rotation period, giving further insight into its physical properties. The significance of this awakening extends beyond the purely scientific. For the public, 3IATLAS represents a tangible connection to worlds beyond imagination, a piece of another solar system briefly passing within reach of our instruments. For scientists, it is a reminder that the galaxy is a dynamic and interconnected place, where stars not only shine in isolation, but occasionally share fragments of their planetary construction with one another. The fact that this comet behaves exactly as theory predicts makes it a perfect test case. Unlike ʻOumuamua, it is not shrouded in mystery or controversy, but instead provides a baseline for what interstellar comets should look like and how they should act. In that sense, it is both extraordinary and refreshingly ordinary, extraordinary for its rarity, but ordinary in its conformity to physics. And yet, this ordinariness is what makes it extraordinary. Every grain of dust, every puff of vapor from 3IATLAS represents material that has traveled untold distances, carrying chemical secrets from a star system we may never see. In a universe where direct exploration of exoplanets remains beyond our reach, interstellar comets like Atlas are natural probes, delivering samples to our doorstep To miss the opportunity to study them would be to ignore a rare and fleeting gift from the cosmos. For now, as telescopes continue to track its growing coma and tail, astronomers remain keenly aware of the narrow window before this visitor departs forever. What it reveals in the weeks ahead may reshape our understanding of planetary systems, chemistry, and perhaps even the origin of life itself. 3IATLAS represents a striking departure from the previous interstellar objects humanity has encountered, not only in its speed and trajectory, but in its sheer scale. When ʻOumuamua passed through our solar system in 2017, its estimated size ranged from 100 to 400 meters, depending on its reflective properties, making it more like a modest asteroid than a grand comet. Borisov, discovered in 2019, was larger, with estimates placing its nucleus around 400 to 500 meters in diameter, and it displayed the clear characteristics of a comet, including a visible coma and tail. But 3IATLAS dwarfs them both. Based on its brightness, corrected for distance and activity, astronomers suggest that its nucleus could be several kilometers across, potentially up to 10 times larger than Borisov, placing it firmly in the category of a large comet rather than a small oddity. The discovery of such a massive interstellar visitor changes the conversation entirely, challenging assumptions about what kinds of bodies can be ejected from star systems and survive the harshness of interstellar travel. The implications of its size are profound. Larger bodies require far greater amounts of energy to achieve escape velocity from their home system. A small rock can be flung into interstellar space through a modest gravitational encounter with a planet or star, but to accelerate a body of Atlas's scale to the blistering 66 kilometers per second it travels today requires cosmic violence on a far grander scale. It suggests that the planetary system from which it originated may have undergone massive upheaval. Perhaps giant planets migrating inward and outward, scattering comets like billiard balls, or perhaps a supernova or close stellar passage, disrupting the icy outer regions of its parent system. The energy needed to send an object of this size hurtling through the galaxy tells a story of chaos, destruction, and powerful gravitational forces at work. In this sense, 3IATLAS is not merely a comet, it is a survivor, a relic carrying scars of ancient cataclysms from another sun. Size also matters when it comes to scientific value. A nucleus that spans several kilometers likely contains layered deposits of ices, organics, and dust, built up over billions of years in its birth system. Each layer may preserve chemical records of different eras of that system's evolution, much like tree rings or ice cores preserve Earth's history. Smaller comets release only a limited sample of their contents when they approach the Sun, but a larger body like 3IATLAS could provide a far richer record, with multiple regions of activity releasing different materials. The coma it generates is already significantly more substantial than what Borisov displayed, and astronomers believe its tail will continue to lengthen and brighten as it nears perihelion. This gives researchers the opportunity to study a broader spectrum of molecules and dust particles, each one a piece of another planetary system delivered to our instruments. The sheer scale of the activity increases the chance of detecting rare compounds or unusual isotopic ratios that smaller comets might not reveal. But size also creates challenges. Determining the true diameter of its nucleus is complicated by the large coma surrounding it. The cloud of gas and dust reflects sunlight, making the comet appear brighter than the nucleus alone would suggest. Untangling the two requires careful spectroscopic measurements, thermal readings, and in some cases radar observations. Instruments like the James Webb Space Telescope, which can detect heat emitted from the solid nucleus even when masked by dust, are essential for refining these measurements. Ground-based radar facilities, though strained by the object's faintness and speed, may provide additional constraints. If the estimates hold true and 3I-ATLAS's nucleus is indeed several kilometers wide, then it represents the largest interstellar object ever detected by humanity, one that redefines the category altogether. The presence of such a large interstellar comet also raises questions about how common they might be. Were ʻOumuamua and Borisov simply outliers, smaller representatives of a hidden population, while 3I-ATLAS shows us the true scale of interstellar wanderers? Or is Atlas itself the outlier, an unusually massive specimen flung our way by rare cosmic circumstances? The upcoming surveys by the Vera C. Rubin Observatory will help answer this by detecting more visitors, but for now, 3I-ATLAS forces scientists to reconsider the range of possibilities. If planetary systems are ejecting bodies of this size into interstellar space with any frequency, then the galaxy may be filled with wandering mountains of ice and rock, silently passing between the stars. For astronomers, the size of 3I-ATLAS is both a challenge and a gift. It makes the comet harder to fully characterize, but provides vastly more material to study. It stretches models of planetary dynamics, but offers richer samples of alien chemistry. It underscores the violence of its origin, but demonstrates the durability of cosmic bodies traveling across unimaginable distances. Above all, its bulk ensures that the story of 3I-ATLAS is not one of a fleeting curiosity like ʻOumuamua, but of a monumental visitor, a massive messenger from another star system, reminding us that the galaxy is a place of scale, violence, and wonder, far beyond what we have yet imagined. The journey of 3I-ATLAS through our solar system has not only expanded scientific understanding, but also exposed the limitations of current astronomical technology, shining light on just how close humanity came to missing this monumental discovery altogether. Despite being dramatically larger than both ʻOumuamua and Borisov, Atlas first appeared to astronomers as a faint dot at magnitude 18.8, over 2 million times dimmer than the North Star. At that faintness, detection required highly sensitive instruments and pristine sky conditions. This reality emphasizes a sobering truth. If an object of this size and speed was nearly overlooked, countless smaller interstellar travelers likely passed through our cosmic neighborhood without ever being noticed. The fact that Atlas was eventually identified shows the strength of survey systems like ATLAS, Catalina Sky Survey, and the Zwicky Transient Facility, but it also highlights how precarious our grasp is on these fleeting cosmic visitors. The galactic background, cosmic dust, and sheer faintness of such objects make them elusive prey, and our current detection technology is at the very edge of being sufficient. The difficulty comes from multiple directions. Ground-based surveys operate under constant interference from atmospheric conditions, light pollution, and seasonal sky coverage. Large telescopes like the Very Large Telescope or Keck Observatory can peer deeper, but their time is limited, and they often rely on alerts from smaller wide-field survey telescopes. Automated systems excel at spotting moving points of light against sparse star fields, but 3I-ATLAS initially passed directly in front of the galactic center, where dense clusters of stars camouflage faint moving objects. This explains why its initial discovery lagged behind its actual arrival by weeks, and why it was citizen scientists who dug through archives to extend its timeline. The comet's path illuminated a blind spot in current systems. Bright, crowded backgrounds confuse even advanced detection algorithms, meaning that significant cosmic wanderers can slip by unnoticed simply due to their unlucky trajectory across the sky. These limitations reveal something profound. If an object as significant as Atlas could be nearly missed, how many more interstellar messengers have already passed us by? Statistical modeling suggests that the galaxy may be teeming with such travelers, ejected from countless planetary systems undergoing violent transitions. The discovery rate so far, 3 confirmed in less than a decade, already implies that interstellar objects are not rare anomalies, but part of a much larger and dynamic population. Detection bias explains why we see so few. Our technology is tuned to the brightest, closest, and most conveniently positioned wanderers. Meanwhile, smaller, dimmer, or more distant objects remain invisible to us. Some may even be present in the solar system right now, faint and unflagged, slipping past our observational net while we focus on brighter targets. The scale of this hidden population could be staggering. Current estimates suggest that at any given time, thousands of interstellar objects, larger than tens of meters, may be passing through the solar system. Most are too small or too dark to be picked up by present surveys. Atlas, with its size and activity, offered astronomers a stroke of fortune. It was bright enough and active enough to announce its presence. Yet it also served as a reminder that humanity's detection systems are only catching the tip of a vast iceberg, and the unseen bulk of interstellar visitors continues to glide silently by. This makes the case for advancing detection technology all the more urgent. The Vera C. Rubin Observatory, once fully operational, promises to revolutionize this field. Its enormous 3.2 gigapixel camera and sweeping sky coverage will allow it to scan the entire southern sky every few nights, identifying moving objects with unprecedented efficiency. With its power, astronomers expect to detect interstellar objects not once every few years, but multiple times annually. This shift will transform our understanding from sporadic encounters to systematic study, allowing for patterns to emerge about size distribution, composition, and frequency. It will also eliminate many of the blind spots that nearly caused Atlas to be overlooked, as Rubin's wide-field images and advanced processing will flag faint motions even in complex star fields. In combination with space-based observatories like the James Webb Space Telescope, these advances will bring interstellar science into a new era. What makes this hidden population so compelling is not just its abundance, but its potential diversity. Every interstellar visitor carries within it the story of its home system. Some may be rich in volatiles, others more asteroid-like, still others composed of exotic mixtures reflecting unique stellar environments. Atlas, with its large size and active coma, provides clues about one type of planetary system, but others will show different chemical signatures, revealing whether the processes that shaped our solar system are universal or rare. Over time, with enough detections, astronomers may be able to map the galactic distribution of planetary system chemistry through the study of these wandering messengers. 3IATLAS's near miss with invisibility is therefore both a warning and an invitation. A warning that our current view of the galaxy's interstellar traffic is painfully incomplete, but also an invitation to imagine the possibilities of what lies just beyond our current reach. With each new detection, the galaxy's hidden population comes into sharper focus. The comet reminds us that we are not alone in our cosmic neighborhood, not in the sense of life, but in the constant flux of material, worlds and fragments of alien systems streaming silently past us. What we have seen so far is only the beginning, and as detection systems evolve, the curtain will be pulled back on a hidden world of wanderers, reshaping humanity's view of its place in the universe. The story of 3IATLAS reaches its most profound moment, not in its detection, nor in the frantic observations it inspired, but in what it ultimately means for humanity's understanding of the cosmos. As this interstellar visitor races back into the dark void beyond our solar system, it leaves behind far more than faint streaks of light on telescope images or pages of dense calculations. It leaves behind a legacy of proof. Proof that our galaxy is alive with countless wanderers, proof that fragments of alien planetary systems routinely cross our cosmic doorstep, and proof that we are finally at a technological threshold where such encounters can be studied in meaningful depth. For centuries, astronomers speculated about whether material from other star systems could ever find its way into ours, and for centuries it remained in the realm of theory. ʻOumuamua cracked the door open, Borisov pushed it wider, and 3IATLAS has swung it wide enough for all of us to peer through. The conclusion we must draw is that interstellar visitors are not rare exceptions, but an ongoing phenomenon, one that future generations of astronomers will treat not with astonishment, but with expectation. What makes 3IATLAS so transformative is the wealth of lessons it compresses into a fleeting passage. It taught us about the raw power of cosmic violence, about the way planetary systems can eject massive bodies during chaotic migrations or stellar deaths, and about the survival of pristine material across millions of years in deep space. It reminded us that the dust and ice locked within comets are more than debris. They are time capsules, preserving the chemistry of alien systems at the moment of their formation. By analyzing the gases, the dust, the spectral fingerprints of 3IATLAS, scientists gain direct samples of another star's building blocks, without ever leaving the comfort of our own system. This conclusion is profound. The galaxy shares its secrets freely, scattering them across the stars, and it is up to us to build the eyes capable of recognizing them. Yet the comet's story also revealed our vulnerabilities. 3IATLAS was almost lost in the glare of the galactic center, camouflaged by billions of background stars. It took not only professional survey telescopes, but also the persistence of citizen scientists to extend its timeline and confirm its trajectory. The conclusion here is equally important. The future of astronomy is collaborative, and the democratization of data ensures that breakthroughs can come from anywhere. In the digital age, discovery no longer belongs exclusively to observatories on mountaintops, but to anyone with patience, skill, and curiosity. The interstellar age of science will be one of partnership, where professionals and amateurs alike share the thrill of unlocking cosmic mysteries. 3IATLAS also forces us to look forward with urgency. Its sheer speed and extreme trajectory highlight how little time humanity has to study these messengers before they vanish forever. The conclusion we must face is that if we want to learn everything possible from these fleeting visitors, we need better technology, faster coordination, and perhaps even spacecraft ready to intercept them. The James Webb Space Telescope has already shown what precision infrared spectroscopy can reveal, but it is limited by time and distance. Missions of the future may launch interceptors designed to collect samples as these objects pass by, bringing back alien dust and ice for laboratory study. That is no longer the stuff of science fiction. It is the logical extension of what discoveries like 3IATLAS demand. Perhaps the most remarkable conclusion of all is how these objects reframe our place in the galaxy. For generations, humanity has thought of the solar system as an isolated bubble, but Atlas demonstrates that this bubble is porous. Material flows in and out across the gulfs of space, carrying with it hints of other suns, other planets, and other possibilities. The chemistry inside these messengers may even whisper about the universal potential for life, as complex organic molecules ride on their icy shells between systems. Whether or not life itself spreads this way remains an open question, but the possibility alone elevates the importance of every interstellar visitor. Each is not just a rock or a ball of ice, but a courier of cosmic history. In the end, 3IATLAS is not simply a comet, nor just the third confirmed interstellar object. It is a turning point. It marks the moment humanity must stop treating interstellar visitors as curiosities and start seeing them as opportunities, perhaps even responsibilities. Every detection is a reminder that we are part of a much larger galactic story, one written in trajectories and eccentricities, in dust clouds and spectral lines. The chase for this particular visitor may be ending, but the age of interstellar object science has only just begun. And as we look up into the night sky, knowing that thousands more are quietly passing by, the conclusion becomes clear: the universe has always been speaking to us. Now at last we are learning how to listen.